So welcome everyone. This is going to be firewalls or switches as a default gateway. My name is Tony Burke. I'm a networking instructor, also a skydiving instructor. But today we're going to talk about networking. And this is about whether or not we're going to use firewalls or switches as a default gateway. Or more general, some of the limitations and advantages of doing firewalls, routing through firewalls versus routing through routers, switches, etc. And also talk a little bit about VRFs. So the problem statement, where is the best place to have a first hop, also known as a default gateway? Is it a firewall or switch or something else? So I've been seeing this question come up quite a bit recently on Reddit and other places, and I thought maybe it might warrant a little bit of a discussion. So I threw together some slides, and I'm going to post this on YouTube. I was going to edit down a more slick way of doing this, but I think this is just as good live. So first hops, just as a definition, next hop, first hop, default gateway. In this context, they all mean the same thing. When we have a device that's on the network and it's got an IP address, it's going to have the devices that are local to that subnet. And then if we want to get out of that subnet, we have to go to a first hop or a default gateway. So most devices, endpoints. So that could be like a virtual machine, could be a bare metal server, could be a tablet, a desktop, a laptop, anything with an IP address and MAC address combination. Typically, we'll call that an endpoint. And then it's going to need a default gateway. In this case, we can go and we're going to configure it that way. Now, there are some rare cases where you'll have an endpoint that's got a routing protocol. So even if it's a server, it's running BGP or something. But we're not going to do that. We're not going to talk about that case here. That's a pretty edge case. We just configure a default gateway, and that's what most devices have. Sometimes you configure it manually. Sometimes you get it from DHCP or some other method. But we need a first hop, a default gateway, to get out of our individual network. So what device is going to be that in our data center? And this is mostly a data center discussion, by the way, but it could be for the campus. So generally for our options for a first hop are either going to be a switch virtual interface, typically an SVI, that's an interface VLAN is another name for it, or a firewall. So those are generally our two options. Of course, in networking, there's lots of other possibilities, but these are generally the two that you're going to see. So if our gateway is 10.1.100.1, where is it going to go? Well, in this architecture here, so this is the traditional three-tier architecture. This was popularized in about 2005, 2006, because that's the year that Intel and AMD came out with server processors that had virtualization extensions that made it practical to take a physical workload and put it into a hypervisor. Before that, virtualization was mostly a toy. It was mostly used in QA and dev, but you would never use it for production. But after we got those extensions, basically when we put a workload into a virtual machine, workload as a virtual machine on a hypervisor, we got about the same performance we would get on bare metal, minus maybe a few percentage. So it made it very viable for us to go in and virtualize just about everything. I don't remember the exact statistics, but something like 0% of production workloads, or pretty close to it, were virtualized in 2005, 2004. And by 2010, something like 80%. So it was it took effect, became very popular very quickly. And so this is the architecture that we generalized, that we settled upon for many years. And it's the three tiers. So core would be our layer 3 only. Our first hop would be on the aggregation layer, typically HSRP or VRFs. And then our access layer would be layer 2. So this would be, do the pen here. So this would be, also there's a connection there. That would be our first hop, is our default gateway. Typically running some sort of first hop redundancy protocol like HSRP or VRFs, depending on your vendor. Then a little bit after that, we would consolidate the core and aggregation layer. We took those two, and then we just consolidated them into the collapse core. So we call this a collapse core. So this is still a common way to do things. And again, there's still, there's a MLAG connection there, or VPC or whatever it is. And that's where our first hop is there. So that's, and again, would be running some sort of first hop redundancy protocol. And then we got EVP and VXLAN, and that allowed us to do a couple of things that we couldn't do with that, such as having more than 2 spines or more than 2 devices at this layer. And here our first hop is on the leaves with what's called an Anycast gateway. So it's the same IP address on all devices. Normally we're not supposed to do the same IP address on multiple devices, but there's some magic that goes on to make it so that every leaf is your first hop for every subnet, which is nice. It's distributed forwarding. So another thing I wanted to talk about is the difference between north, south, and east, west. I think most of you are probably familiar with the differences between the two. North, south is the traffic to and from external networks, and east, west would be traffic between endpoints in the network. So our first hop choices, generally speaking, not always, but generally speaking, is going to be SVI on the switch, Anycast gateway, or first hop redundancy protocol, or we'll put it on a firewall. So let's talk about the considerations for doing either one of those. When we do in a switch, we do what's called hardware forwarding. And hardware forwarding it's done in the ASIC. And I don't really like the term ASIC because ASIC can mean a lot of different types of technologies. I generally prefer the term forwarding engine. So for example, the Broadcom Trident is a forwarding engine. You can also call it an ASIC or a switch on chip. That is the heart of many of the top of rack switches from many of the vendors. So Cisco, Arista, Juniper, they all have Broadcom, Trident 3, Trident 4, Trident 5 based switches. Cisco wants them. Some of the vendor will make its own ASIC or FE, and Cisco has a couple of their own. There's cloud scale ASICs and so forth. So what makes them so special? Well, it's the way that the forwarding is done. So when a packet or frame comes into one of these devices, we need to figure out what to do with it. So we need to do a lookup in the forwarding table, whether that's an IP forwarding table or an Ethernet forwarding table. Something has to have the addresses and the networks that we know, so that the packet knows where to go. And forwarding tables in these forwarding engines, these ASICs, are stored in what's called CAM memory, TCAM, or something equivalent to it. Basically, it's very, very fast. And the requirement here is when a packet or frame comes in, we need to make a forwarding decision before the next one arrives. So we certainly have less than milliseconds. We have less than microseconds or even nanoseconds, depending on the interface speed. Remember, the faster the interface, the shorter amount of time we have to make a lookup. And so this is very fast lookup memory. It's limited. It generally draws more power, so that's why it's limited in the forwarding capacity, but that's what we're going to use. But this allows us to do basically line rate out of every interface. Now there might be some exceptions, like some forwarding engines can't forward all packet sizes at line rate. When you get to the smaller packet sizes, it might start to struggle. If you have like every packet is 80 bytes, then it maybe can't quite do line rate. But for your average workload, it's going to be able to do basically full on out of every interface with no problem. But these devices are very limited in functionality. Basically, all their functionality is baked into when the chip was made. So when the chip was manufactured and designed and it comes off the assembly line, that's all it's ever going to be able to do. Whereas software forwarding, that's what firewalls tend to do. Now, they might have some hardware offloads, but generally, the forwarding is done by the CPU. So a packet comes into these devices, and then something happens to that packet. The forwarding table is stored in RAM. The rules are stored in RAM. And we generally can't do line rate out of a lot of ports. Maybe like 2 1 gig ports, not a problem. But 48 1 gig ports, your average server that has a general CPU, like an x86-based CPU, is not going to be able to run line rate out of all those ports. But the functionality is nearly limitless in terms of what can we do with them. Because just software, we just compile some new software, add it in, and then we've got new functionality. So those are some of the trade-offs we have here. And just to put a finer point on these trade-offs, let's check out a difference in forwarding rates. So I picked 2 devices, and I just kind of picked them at random. And this may not be indicative of all devices or the devices that you're involved in, but I just wanted to point out some of the biggest differences here. So I picked the Cisco Nexus 93180YC FX3. That's kind of a mouthful, but it's a pretty typical top of rack switch. We've got 48 ports of 25 gigabit per second capability. So 48 by 25 gigs plus, do it mathematically here in the parentheses, you have 6 times 100 gig, or sometimes some of the newer ones have 6 times 400 gig. Or they might have 8 times 100 gig or 8 times, pretty typical. And if you do the math, you get 3.6 terabits per second. So this switch, and it on average it runs about 325 watts, is capable of 3.6 terabits per second, fully maxed out. Now you're probably not going to run it fully maxed out, but that's a lot of capability. That's a lot of capacity. So basically, we're almost limitless in terms of our forwarding capacity. Now, we are limited by our uplinks, and we might be oversubscribed and some other stuff. But in terms of from one port to another port, the switch itself is not going to be the bottleneck. Now, compare that with the Palo Alto 5445. I think that's what I picked out here. And it runs about 630 watts on average, and we could do 90 gigabits per second of app-aware forwarding. So different firewalls have different capabilities, but a lot of them ones would be considered next-generation firewalls or app-aware firewalls or whatever. But they can look at the payloads in addition to the headers. And if you compare the two, I mean, 3.6 terabits per second and 90 gigabits per second, that's about 3% of the forwarding rate. So that switch can forward way more times the amount of traffic than that Palo Alto. It's like, I can't remember what it is. It's like 400 times, something. I mean, no, not 400 times, but it's quite a bit. Actually, let's do a little bit of math here. So 3.6 divided by, what was it, 80? 90. Divided by 90. That's 40 times the capacity rate, or 3% of the forwarding rate, depending on how you look at it. So that's pretty substantial. And that's just, depending on your firewall, depending on your switch, those numbers can vary quite a bit. But generally, you're going to find that your firewalls have just a small percentage of the forwarding capability of a switch. Now, let's flip that in terms of what they can do. So there are security capabilities. So the Cisco Nexus 93180YC FX3 is like a lot of the other switches. In fact, this is almost universal. The only thing that they can do is what's called stateless ACLs. So they can evaluate the layer 2, layer 3, layer 4 headers. They cannot go into payload, and they can't build a state table or a connection table. So they're very limited in the security, while as the Palo Alto has nearly limitless capabilities, at least in the platform. And you can add to the functionality pretty easily. Whereas the switches, that's all it's ever going to be able to do. So what is a stateless ACL? Well, generally multi-layer switches. So most of the switches from the vendors, Juniper, Cisco, Arista, and all the others, the switches that you're likely to find in a data center or in a wired campus, usually in the wired campus, but almost always in the data center, are going to be known as multi-layer switches. These are switches that could do layer 2 and layer 3. So then they could forward about the same rate. So many switches can do this today. We generally don't even say multi-layer switch. It's kind of redundant. But generally, multi-layer switches can evaluate traffic based on the layer 2 headers, the layer 3 headers, and the layer 4 headers, and that's it. They can't go into payloads. So when a packet enters a switch, we can allow or deny traffic based on those headers, and maybe a couple of other parameters, but that's pretty much it. But switches don't remember what they did with the previous packets. So a firewall can remember. So a firewall will generally build a connection table. That's a basic functionality of any layer 4 stateful firewall. That's the state and stateful. So how do we know that there's a connection? Well, the firewall saw the SYN, SYNAC, ACK in a TCP connection, and it's going to put it into its forwarding table, into its state table rather. So when it sees a TCP segment come in, it's got the established bit set, but did someone just send a segment with an established bit without doing the TCP SYNAC ACK? Well, the firewall can tell because it's got a connection table. It's going to look at the source and destination port combination and know, yes, we've got a open TCP connection, so let that one through. If we either haven't seen a TCP SYNAC ACK or TCP connection initiation, or at some point we saw a close or reset, then that established bit's going to get dropped. A switch will see the established bit and just let it through. It didn't know that there had been a previous SYN, SYNAC, ACK exchange because it doesn't remember anything that happened for the previous packet that came in. And also switches can't go into payloads, and they can't build state connection tables for ACLs. So that's why we call an ACL stateless. And this is true for all the switch vendors. So not just Cisco, but also Arista, Juniper, Cumulus, etc. Firewalls, and other terms, they can vary widely in capabilities. So I'm being very general on their capabilities, but generally they can allow deny based on the layer 2, layer 3, layer 4 headers, just like a switch can, but they can also build the tables, the connection tables, the state tables. And then most firewalls today can go into the payload and are app aware. So they're familiar with various protocols. So they can look for things like SQL injections and cross-site scripting and other things that might be hiding, nefarious things that might be hiding in the payload. But the trade-off there is that more firewall rules can sometimes lead to more latency because it's got to do more work in every packet, and then more limited forwarding capacity like we talked about before. So these are all trade-offs. So if we have a first hop on a switch, so typically a lot of the networks being built today are going to be EVP and VXLAN, and they use what's called an anycast gateway. So that means that the first hop's going to be on all of the different leaves. So we've got one here, same IP address, and then it can be also the first hop for multiple segments, multiple networks. So in our case, we have two endpoints. One's on 10.1.100.11 and one's on 10.1.200.12. And they both have their default gateway. Their default gateway is their local leaf, which is really nice. So traffic can flow between the hosts as fast as the link speeds allow. So unless we have some congestion, which we're probably not going to have if we do the network right, then that's not going to be the switch platform is not going to be the limiting factor. However, if we put a firewall in between the endpoints, then we've got to route through that firewall somehow. We've got to pass the traffic through. And generally, one easy way to do that is just to make the firewall the default gateway. Now, there's some other things that we could do. We could do policy-based routing. But generally speaking, the traffic is going to have to go through the firewall, no matter how we set it up. And then, so like traffic between endpoint 1 has to travel to its default gateway or PBR or whatever. We'll get it to there. The firewall will evaluate it, send it onto endpoint 2 if it allows it. It responds and then comes back. Now that firewall becomes a bottleneck. So we have this big network with all these 25, 100 gig, 400 gig interfaces, and then we're limited by what that firewall can push. So that will become a bottleneck depending on how much traffic we're pushing. Now, if you're not pushing more than whatever the firewall can do, it's probably not a big deal, but it might be. So there's a trade-off. Switches forward at line rate, but provide rudimentary security capabilities. We can do ACLs. That's another thing I forgot to mention, is that we can do ACLs on these ports, on these networks, but they're kind of hard to keep up to date. So a lot of times, if we're going to be doing it this way, it's just any. Again, we can put ACLs if we want, but they're a little bit hard to manage. Whereas a firewall being centralized, they usually have pretty good tools in order to keep those firewall rules up to date. Although, the joke is that firewall rules never decrease in size; they only increase over time, and we never go back and remove the ones we don't need. But that's a whole other discussion. So switches forward at line rate, but provide rudimentary security capabilities, if any, depending on what we use. And then firewalls provide excellent security capabilities, but a much lower forwarding capacity and can easily become a bottleneck. So what are the approaches to this problem? Number one, just use a firewall only for the north-south traffic. So in this case, I would have a firewall here, and this would be my internet or my external networks, whatever it is. And then all of my north-south traffic coming in and out of the fabric would go through a firewall, because we want to protect that at least. And then inside the fabric, everything is just any or rudimentary ACLs. So that's one approach. That's a pretty common approach, actually. Another one, much less common, but I have seen it, is you just buy enough firewalls to service the capacity that you need to service. So that means typically buying tons of firewalls, and that's going to be a lot of money. And there's still going to be a bottleneck, but at least you've got your east-west traffic being protected as well. But more often than that, and something I'm seeing more and more of, is a compromise where some east-west traffic is firewall forwarded, and some is switch forwarded. And we can do that with VRFs. So here's a pretty common compromise. And I like this. This is generally where I start. So if I'm brought in to help design a network, this is kind of my starting point. Unless there's some specific requirements that might make this unfeasible, this is a good way to start, because intra VRF traffic is switch forwarded. So maybe some ACLs, maybe not. But inside of the VRF, it's switch forwarded. And then from one VRF to another, it has to go through a firewall. So our VRFs become our security zones. So we might have a separate DMZ security zone, a separate security zone for our databases. Maybe different apps have their own security zones. And then where we keep most of the east-west traffic forwarded by switches, and then some of the east-west traffic will be firewalled. And of course, the internet here, all that traffic will go through the firewall, of course. So this is usually what people do, or I'm seeing this more and more common. This is what I typically default to. And it's a nice compromise, I think. If you absolutely have to have all traffic east-west be evaluated by a firewall, that's going to be a lot of firewalls, or you're not going to have a lot of traffic. So that's one extreme. And then just doing everything east-west open and forwarding through switches, that's another. It's not really an extreme. It's more common than buying a firewall for every VLAN, but I think I like this. This is a nice compromise. So that's it. That's it for the stream. That's it for the presentation. Hope you enjoyed. If you have any questions, you can let me know down below in the section down there, in the comments section. Let me know in the comments section if you have any questions.